Now let us see some of the regions available in the state space. One is local maximum. A state which is better than its neighboring state is known as local maximum. We have seen in the figure, suppose this be our hill, then if this is our state, current state, then all the neighboring states, let it be here or here or here, all are having a lower value when we compare that with the current value. Such a point is known as a maximum. If it is not the global maximum, global is the maximum height in a hill. If it is not the global maximum, we treat it as local maximum, right? So I have already told what a global maximum is. Then we have plateau or flat local maximum. When the succeeding states have the same value, when we apply operations on a state, it generates an equal value not only for one operator but many operators available on that state, then we call it as a plateau. So from here we are generating an operator, we could get another state. From there we are again operating, we get another state. All these have an equal value, then we call it as a plateau. So flat region where neighboring states have the same value is called as a plateau. Then ridge, when we have small hills where the top of all the hills are equal, then we call it as a ridge. That is the point the neighbors have itself a slope, a downward slope. We call it as a hill. When the size of the hill is so small and which is getting repeated over an area, then we call it as the ridge. It's a special kind of local maximum, because when we consider a point, let us see the slide before. When we consider a point, let it be this, then surrounding this area all have a lower value, which is similar to the case with this. So since it is not the global maximum, we can consider the topmost point of this ridge as local maximus. Okay. Then you know what a current state is. We can apply the operators only on the current state. Then shoulder, it is a plateau that has an uphill edge. That is called a shoulder. The flat can have an uphill edge or a downhill edge. See this. This is a flat surface. This is another flat surface, but they are different. After this, we are having an upward movement. So this is known as a shoulder, while this is not a shoulder because we have a downward movement after the terminal point of the flat surface. So this is a shoulder, this is a plateau. A shoulder is also a plateau. It will be having an edge or upward edge at a terminating point of the flat surface. All these regions create problems in the hill climbing algorithm. Let us see some of the problems and how can we solve these problems. We'll be discussing in 2 or 3 slides. So hill climbing cannot reach the optimal state or the global maximum if it enters any of the following regions. That is, if we are entering any of the regions, we are stuck in that region due to the property of the algorithm, so that we will be considering only the immediate value for proceeding in the upward movement. So that will not be possible if we are stuck in these regions. Let us see how it works. Let us consider local maximum first. At local maximum, all neighbor states have a value worse than the current, because that current state will be the highest value. If we consider that local area, then hill climbing using greedy approach will never accept a worse value, because greedy approach will always pick up the best value available. So at this point, we will not be able to move further because all its succeeding states are having worse values, or a value which is lesser than the current value. The process will end even though a better solution may exist. So we have a global maximum, but unfortunately we fell into the local maximum. Due to the greedy approach, we cannot move further, so that we will not be able to reach the global maximum at any cost. To overcome this local maximum problem, we can do another trick by using backtracking technique. So we are moving backward, which is not a part of hill climbing, but in order to escape from this local maximum, we have to move using some other technique. For that, we will be maintaining a list of visited states. So we are considering another list. Whichever states we have visited will be entered in that list, and by picking those lists, we can go back to a previously visited state. From there, we can select a different path for proceeding, so that we will not be reaching this local maximum. That's how local maximum problem is solved. Then plateau. On a plateau, all the neighboring states will be having the same value. So we will not be able to select a best value because all the values are same. To overcome this problem, we will make a big jump. Instead of selecting the consecutive values, we will be ignoring all these values and select a higher value. Randomly select a state which is far away from the current state. So in this jump, there are possibility that we will be landing at a non-plateau region. We cannot say that it is an optimal or it is a climbing hill, or it may also be a lower height if we make a jump. So by making a jump, we are moving away from the flat area. Then ridge. Here also, if we move from a top point, all the succeeding or adjacent neighbors are in the downward path. Hence, the algorithm cannot move further. For overcoming this ridge, we will be using 2 or more rules before testing. Let us see the figure. So how do we proceed in a hill climbing algorithm? we are using generate and test procedure. We will be initiating an operation to produce a new state, and we have to check whether that state is a better one or which is a goal state. Then if it is, we have to move into that portion. In this spot, if we generate another state, we will not be getting a better value because it is part of a ridge. So we are not able to move further. So instead of testing at each location, we will be generating so many points, and after that only we make a testing operation, because testing operation will be the condition for us to proceed or to stay at that location. So before testing, we will be generating so many states near to the current node, and afterwards, suppose there are 1, 2, 3 states and 4, 5. We are making 5 state generation. Then only we are making a test so that we can bypass equal values. So in that way, we can escape from a ridge property. So testing is not done after generating each state. Another one is simulated annealing. A simulation means it is an imitation of an operation of real world. If we are able to imitate the operation what is followed in the real world, we can say that it is a simulation. So we are dividing this word into two parts, simulation and annealing. Annealing is a part of metallurgy, which is again a part of material science. This is a scientific property which is a heat treatment operation which alters the physical and sometimes chemical properties of a material so that we can change the property. Suppose we have a hard material like iron or metal, then when we heat this, it can be made into different shapes, and we are cooling that. After making those changes, we are cooling the material to reduce the temperature. Once it is cooled to normal, we can get the material in a new form. This process is known as annealing. The same process can be applied in heuristic climbing also. So that is called simulated annealing. It is a modeling by using simulation and annealing by changing the property. So that is explained in a video. You can watch that video after this slide. These two properties are combined in AI to remove some of the problems faced in hill climbing. That is simulated annealing.